Ladies and gentlemen, Professor Bassam Shakhashiri.
Boys and girls, ladies and gentlemen, welcome to the 13th annual Christmas lecture. Among our guests tonight are students and faculty from the University of Wisconsin-Madison, school children from the Madison area, parents and other members of the community. I am pleased to have as my special guest tonight the Dean of the College of Letters and Science, Dean David Cronin. This special event is aimed at people of all ages. I want youngsters and adults alike to learn a few things about chemistry and about what chemists do. Chemicals are all around us. The food that we eat is made up of chemicals. The air that we breathe is a mixture of chemicals. Our own bodies are made up of chemicals. The medicine and drugs that we use when we are sick are nothing but chemicals. And so chemicals are all around us. Chemists do experiments in order to understand the behavior of chemicals. We study chemical reactions so that we learn how to control them and how to put them to good use. All chemicals are safe to handle if we obey the safety regulations. Safety regulations call for us to wear eye protection whenever we do experiments. And that's why I'll be wearing these safety goggles throughout the rest of this program. In addition, I have a fire extinguisher available, which will be used only if needed. This fire extinguisher is available, as I say, to be used only if needed. I hope we will not need it tonight. As we handle chemicals, we should be fully aware of their potential hazards so we don't injure ourselves, other people, or the environment that we live in. Now, doing chemistry can be a lot of fun, and that's what I hope we will have tonight. I want you to sit back, to relax, and to enjoy the festivities, and I want you to try to make as many observations as possible. Look for color changes. Look for changes in volume. Watch out for explosions. And think about what you see and what you hear. And be very careful in paying attention to what I do and to what I say. Now, if you are ready, I'm ready. Are you ready? Yeah. All right. So let's begin then by looking at the properties of some material that are gases. Now, gases are quite useful chemicals. We all know about the use of natural gas to heat our homes. And so natural gas is a chemical substance called methane. As you probably know, that substance is odorless, does not have an odor. But the gas company adds a chemical to it in order to allow us to detect the presence of gas if there is a leak. And so natural gas, which is methane, is quite odorless. We cannot smell it. The additive is what we smell. And so what we will begin to do now is to work with some of the natural gas. And I have this big wand over here, which is actually a big torch. And you'll see that when I light it, there it is. There is natural gas burning. This chemical reaction that we're witnessing here is called combustion. Combustion is nothing but a reaction of a substance with air. Now, combustion reactions are all exothermic reactions, which means that they release energy to the environment. This release of energy is what makes it possible for us to heat our homes, to heat this building, to heat this room that we're in now. Now, some gases undergo controlled combustion reactions. This is an example of a controlled combustion reaction. Other gases undergo very rapid combustion. In other words, they go out of control, and those reactions we call explosions. And that's what we're going to see now as we look at these balloons that we have around us. Now, these balloons clearly contain gases that are lighter than air. That's why they're held up in the air and held to the table by these strings, which you may not be able to see, but you can see that the balloons are not all the way up to the ceiling. So we will begin by trying to set these balloons on fire to find out if these balloons contain gases that undergo combustion. So we'll start off with this blue balloon over here. We'll look at this balloon. It's lighter than air, as we said before. We put the torch to it. I notice some of you are covering your ears. Are you expecting an explosion? Well, that might be a good thing for you to do, but you see, we do experiments in order to find out what's going to happen. So, are you ready for the experiment? All right. We'll begin with this balloon. And you see all that has happened is that the balloon popped, and the gas that was inside the balloon, which is lighter than air, did not undergo a combustion reaction. Now, the balloon that I have over here, this pink balloon, this balloon contains methane. And methane is natural gas. And so what we want to look at now is what happens when the combustion of methane is not controlled. In this burner here, it's undergoing controlled combustion. But we'll watch here and see what happens. So you pay close attention. We'll see what happens here. And you see, there was a very big flame. And that's why it's very dangerous if you have a gas leak at home. It's very dangerous for you to start anything, strike a match or spark anything. It's extremely dangerous. So methane, we know, undergoes combustion and can be controlled, also can go out of control. Now, let's move on and look at this yellow balloon over here. This yellow balloon has a gas lighter than air. And we'll try to put the torch to it and see what happens. So are you ready? Yeah. All right. And you have your ears covered? OK. Now, this gas that we just exploded there is hydrogen gas. Hydrogen gas undergoes combustion very rapidly. Now, there was a big flame. And what I would like to do now is to show you this flame in slow motion. So let's look at a replay of this experiment and look very carefully at the flame as it explodes in the mixture of hydrogen. So if you look with me now, watch, you'll see the reaction in slow motion now. Watch the big flame. And there we go. That was the same flame we just saw here, except we're showing it to you in slow motion. So we've learned so far. You like that? All right. What we've learned so far, I hope, is that methane undergoes rapid combustion and hydrogen undergoes rapid combustion, and therefore we should keep flames away from those gases. Now, this red balloon that we have here, we shouldn't let it just sit there by itself, should we? This balloon, I will tell you now, this balloon has a mixture of hydrogen gas and oxygen gas in it. And this mixture is very highly explosive. And this mixture, because it is highly explosive, it will not only generate a big flame, but will also generate a lot of sound energy. And as such, I would like you to cover your ears, all right? So here we go. Are you ready for this? Now, this example of a combustion reaction between a mixture of hydrogen and oxygen also produced a flame and a lot of sound energy, more sound energy than the combustion of hydrogen. What we should do now is try to look at, again, the slow motion of this explosion to see if we can tell the difference between the combustion of the hydrogen and the combustion of the mixture of hydrogen and oxygen. So let's look at this again and watch very carefully. Here we go. Watch it. There comes the flame to it very slowly. And boom, there you see there's the loudness of the explosion you can't hear, but you can. But of course, of course, you saw that the flame had a lot of different colors to it. So let's move on to something else now and look at some other properties. We'll turn off this source of natural gas here. And that leaves one balloon here. This balloon actually that had the gas that did not burn, this balloon contains the gas helium. And you all know that helium balloons are used for a variety of purposes, including doing experiments of the type that we're doing here. Now I want to show you a different property of helium. Now you know when we talk, our vocal cords vibrate, and they send a great deal of sound energy. Now, what we vibrate, when the vocal cords vibrate, the gas molecules are pushed, and the sound energy is created so that the ear then picks it up. So the identity of the gas in which the sound energy travels makes a difference in terms of the pitch of the sound. And so what I have here is a cylinder that has in it gaseous helium, and I'm going to do an experiment, and you watch very carefully and also listen carefully so you don't miss out on what's going on. So you see the helium is coming out, and this is an experiment where I'm going to substitute the air molecules in my throat with helium. Okay, so you watch very carefully now and listen carefully. My name is Bassam Shakhashiri. And you see, hello, can you hear me? Can you hear me? You see that the change in pitch took place because we've changed. Am I back to normal now? I can't tell. You tell me. The change in pitch is due to the fact that we have replaced the air molecules by the lighter molecules of helium, and that's why the change in pitch took place. Now, we'll take this balloon and do a couple of other experiments with it, and I want you to watch very carefully as I do this experiment. We'll do this experiment over here, and what we will do is take a very cold substance, which we'll talk about shortly. This cold substance is a liquid. It's liquid nitrogen. And what we'll do is add the liquid nitrogen to the balloon. And you see, because of the cold temperature, the balloon collapses. And the balloon collapses because the helium inside the balloon has been slowed down, and the pressure changed because of the change in the temperature. Now, as the helium balloon warms up, of course, it increases in size again. And if you watch this carefully, you see that the balloon goes all the way up to the ceiling because I've taken it off. Now I've taken the thread off. So in using this liquid nitrogen here that I want to talk to you about, I want to do a few other experiments with liquid nitrogen, but I need to replenish my supply of liquid nitrogen. And so if one of the University of Wisconsin students can help me by bringing out a replenishment of this supply, I really would appreciate it. Oh, well. Thank you very much, Bucky. Thank you, and welcome to this special lecture. Thank you for bringing this over here. You see, you're very popular, and you're quite a big hit here. Now, Bucky, I know that you're quite busy with final exams coming up and with Christmas vacation coming up, but I wonder if you can stay for the duration of this lecture. Can you stay? I know good. I know the athletic teams have been doing quite well, both the men's athletic teams and the women's athletic teams, right? Right, I know that, yeah. I know that among other things that you do, at least I heard that you badger the cheerleaders. Is that right? You don't? No? Bucky, I'll tell you what. We have a whole slew of experiments we're going to do here, and I'd like you to help me out, but I see that you didn't bring your safety glasses with you, and you don't have any safety goggles, so I'll ask you to stick around and just watch. Is that all right? I know it, darn it, I know it. Let's sit around here, okay? I have a special seat reserved for you over here. Okay? So we'll continue to work with. Are you comfortable, Bucky? Great. All right. We'll continue to work with liquid nitrogen. We've got more liquid nitrogen here. And liquid nitrogen is used in a branch of science called cryogenics. Cryogenics is the branch of science which deals with the study of the properties of material under very cold temperatures. And so this is what we're going to do now, do a variety of experiments with this liquid nitrogen. And you see I can just pour it down here. The boiling point of liquid nitrogen is minus 196 degrees Celsius. It's very, very cold. And that's why we keep it in this thermos bottle in order to prevent the liquid nitrogen from evaporating. So we will do a variety of experiments with this. And these experiments include working with this substance. Now, this substance that I have here in this bottle is nothing but the element mercury, which is a liquid at room temperature. The element mercury freezes at a temperature of minus 39 degrees Celsius. And what I have done is prepared ahead of time a small item which I will use to do the experiment. This item is using the element mercury. This item is, as you will see very shortly, a mercury hammer. You see, it's quite hard. We keep it in this cold liquid here so it stays frozen, so the temperature there is below 39 degrees Celsius. Now, what I have here is some examples of some samples, I should say, of small pieces of rubber. And you can see that these small pieces of rubber are quite flexible. And what I'm going to do is take these pieces of rubber, put them in this beaker. I'll leave one out here so we can see that it is still flexible. We'll take some liquid nitrogen and add the liquid nitrogen to the rubber. And we'll see what happens. Clearly what happens is that the liquid nitrogen boils because the temperature of the glass beaker and of the pieces of rubber is higher than the boiling point of nitrogen. That's why it's boiling off. At the same time, the glass beaker and the small pieces of rubber are being cooled off. And so what I will do now is wear some hand protection in order to prevent frostbite from occurring. And what we'll do is take some of these, pour the liquid nitrogen over here, and then come back over here. See, pour them out. And what we have is some very hard pieces of rubber, which I will use this mercury hammer to drive in these rubber nails. Now remember that I had one piece of rubber that I didn't freeze. This is this one. And you see I can't pound it in because it's not hard. So we'll pound out a couple of more. And so these pieces of rubber are actually being used now as rubber nails. Now, there are more serious applications for using cryogenics than the ones that I have just showed you here. But I'm going to show you one other experiment, which I think is of interest to people at the University of Wisconsin because it has very direct practical applications. But let me show you the experiment first, okay? The experiment means that I have to come around, so I'll come around and show you this. This experiment involves using another form of rubber in the form of this rubber ball, okay? So everybody can see the rubber ball. It's quite bouncy. It has a very soft texture to it, and it has the characteristic rubbery properties. So what I will do is take this rubber ball and put it in this small thermos bottle and add to it some liquid nitrogen. And of course, the liquid nitrogen will boil. More is better, right? So let's add more. And as the rubber ball is being cooled down, the liquid nitrogen boils off. And if you look very carefully, you begin to see the rubber ball, which tells us that the rubber ball is what? Denser than the liquid or lighter than the liquid? It's lighter because it's floating, right? All right, so what we'll do now is try to take this rubber ball out, and I'll use these to get the rubber ball out. It's quite cold in there. You have to be careful about this and handle this very carefully. Oops. And then ask you to watch very carefully as I try to drop this on the floor. You ready? Okay, here we go. And you see the rubber ball, which was quite bouncy, shattered all over the place, right? Now, I'm going to try to show you. We'll see if we can show you this again in slow motion. So let's see if we can see the rubber ball, which is frozen, shattering in slow motion. So we'll look for this, and here we go. Watch the rubber ball being dropped. You see there, it shatters into very small, sometimes not so small pieces, but see they're not all that small. Okay, so this experience with the frozen material in the area of cryogenics has been put to a very direct application by one of the professors in the Department of Mechanical Engineering. Professor Brayton has developed a method for recycling old automobile tires. And so by freezing them and then crushing them, then the rubber, the frozen rubber, after it warms up, then can be mixed with asphalt and can be used for resurfacing roads. And this has been one of the most important applications in terms of recycling old tires. Now, we'll move on to more experiments in this area that involves working at very low temperatures, at very cold temperatures in the liquid nitrogen range. And as we try to look at some more experiments.
Merry Christmas! Merry Christmas! Hey!
Welcome, Santa. Welcome.
Hi, Doc. How you doing?
Fine. How are you?
Good, good.
I'm so glad that you were able to stop by.
Yes, yes. I was glad to see all the children here. And these children, you know, they're not afraid. A lot of children are afraid of Santa Claus. This is a very common phenomenon. We call it claustrophobia in the business. Anyway, I'm very happy to be here in University of Wisconsin-Madison. I'm delighted by the lovely December weather you have here. It's so nice and warm. Why, up north, it's really cold up north. I'll tell you how cold it is. I want to describe, we just had our homecoming football game, UW/North Pole versus University of Greenland. And I want to tell you how cold it was. The fans, you could see their breath. There was ice all over the place. Men with beards were frozen. The instruments were frozen. The wind chill was minus 40 degrees. Now that's either Celsius or Fahrenheit, right? Same temperature? Okay. It was really cold.
Well, Santa, that does not sound to me like it's very cold, because it sounds like the temperature where the Wisconsin Badgers play or the Green Bay Packers play.
Yes, but we play in a domed stadium.
Oh.
That's how cold it is.
Oh.
Anyway, I brought you a gift, Doc.
You did?
Yes,
A special gift?
a special gift.
Am I going to like it?
You're going to love it.
Will I be able to use it?
You will be able to use it.
All right, I'm ready.
Old Santa was checking over his list, checking it twice.
Yes,
you know,
yes.
And he found out that you are very interested in getting some computing facilities for your education program here.
Yes, indeed.
And so I contacted my friends on the Hill at UW/administration.
Yeah.
And I asked them to let me work on the first portion of your program. And they sent the money, they managed to dig the money up, and I got my elves working right on it. We don't call them elves anymore, we call them subordinate clauses in the business. But I want to show you, this is a dandy. Here's your first generation computer here. And you just move those little numbers along right like there. And I don't know when the rest of it's coming. The administration was a little shaky on that. But there is more coming, and there's an instruction manual if you need it, you know. Even a little Abacus Tips workbook that you can buy with it, you know, that sort of thing. So that's just for you. And I have a little help for the students, too. Of course, there's too many of them, and I'll see many of them later on, or I won't see them, but I'll come to visit them. But I want to help them out with their final exam. And I want to give them a little help to remember some very important chemistry. Now all of you learned that water dissociates into protons and hydroxide ions. See, Santa knows some of this. Well, in our labs at UW North Pole, we take 3 water molecules and we get 3 protons plus ho, ho, ho. And I'll give you one other tip before I'm through here. I was talking the other day to my cousin Worthy, and he told me why they call the periodic table the periodic table. They call it that because students look at it periodically during an exam to see if they can come up with the right answer. That's why they call it that, believe it or not. My cousin Worthy's an interesting fellow. He's quite into the Christmas business, as the whole family is. And he's a bell ringer for the Salvation Army at our new shopping center up there, Icetown Mall. And he's very good at it, and he's very well known. And people come by and they say, "There's a Worthy clause if I ever saw one." That's right. It's my cousin Worthy.
Santa, I know you have a lot of other lines that you want to share with us, but I want to save some of the good ones for myself. And I know you're quite busy, but can you join our special guests tonight and stay for the rest of this program? Well,
sure.
Great. Why don't I ask you to sit over there next to Bucky?
Oh, great. Hi, Bucky. How you doing? Oh, I don't think I can get that. No.
Moving right along here, I want to continue with doing some experiments at the very cold, under very cold conditions. And what I have done already is liquefy some gaseous oxygen. We took gaseous oxygen and changed it into the liquid form. And that's what I want to show you right now. Here's a sample of liquid oxygen. And if you look very closely at it, you'll see that it's blue in color. The boiling point of liquid oxygen is minus 183 degrees Celsius, so it's quite cold. And liquid oxygen has a lot of interesting properties. And I want to show you some of these properties right now. Now, in order to show you some of these properties, I'm going to move over here where I have a very strong and powerful magnet. And this magnet has, of course, 2 poles to it. I put my penknife here and see it's a very strong magnet. Whoops.
Hey, Doc, which pole is the North Pole?
Santa wants to know which one is the North Pole. Well, one of them is the North Pole, and the other one is the South Pole. Now let's see what these poles... Let's see what happens when we pour some liquid nitrogen in between the poles of this strong magnet. You see the liquid nitrogen runs right through, and nothing really spectacular happens except that the nitrogen splashes all over the table. Now, if we take the blue liquid, the liquid oxygen, and pour it between the poles of the magnet, you see that the liquid is held between the poles of the magnet, indicating that this liquid has paramagnetic properties similar to the properties of the pocket knife that I used before. So it's held there until it evaporates. Remember now, the liquid oxygen boils at minus 183 degrees Celsius, and it's held there, as I said, until it evaporates. And that's a very unusual phenomenon, very unusual in the sense that, as far as I know, this is the only liquid that exhibits this property. Now, liquid oxygen can be used for other purposes, too. And I want to do a couple of more experiments here. We'll take Santa's goodies out of the way here. Now, one of the experiments that I want to do with liquid oxygen involves preparing a liquid oxygen cocktail. Now, usually people have a cigarette or some other smoking material when they drink cocktails, and so I'll try this. I know there's a city ordinance against smoking indoors here, but this is just for the cause of science, right? People actually like this? Now, this cocktail, the liquid oxygen cocktail, is very, very potent. It's so potent, I'm going to show you how potent it is. When we take this cigarette and put it in this beaker over here, you'll see that if I take the liquid oxygen and pour it, you see that we have complete combustion of the cigarette. And I personally think that's what we should do with all cigarettes. Now, this was such a spectacular combustion process that we're going to try to look at it again in slow motion. Right? So let's see how the combustion of the cigarette takes place in slow motion. Watch out for the flame. Watch out for, there we go. We pour the liquid oxygen in, and there goes the flame. Very spectacular chemical reaction. And it is a combustion reaction which is completely out of control. All right. Now, what we want to do is come back and let's look again at the other properties of liquid nitrogen. I want to go back to liquid nitrogen, and I want to take this beaker, put it over here, and then take what I have here. If you watch very carefully, I have an egg. Can you see the egg here that I have? I'm twisting around like that. All right. See? Now I'm going to put this egg very carefully in the liquid, in the beaker, and add to it liquid nitrogen. So we add liquid nitrogen. And of course, the liquid boils off, as we have seen all along. We'll let that cool down for a while. We'll come back to it. Well, let's add a little bit more first. We'll come back to it and do some more experiments with it. I need some more liquid nitrogen, so I'll come back and replenish my supply of liquid nitrogen here. Whoops, we've got to be more careful here. And as we wait for the egg to cool down, we're going to do another experiment with liquid nitrogen, namely to take this flower. Isn't that pretty? Very pretty. I'm going to put this in liquid nitrogen. Now, I know that we have a lot of friends in the audience here, but I have a very special friend in the audience. Everybody is special, but this one is really, really special. And in fact, just earlier this month, she had a very nice birthday, and she invited me to her birthday. And so I'm going to ask her to come out here and take a look at this flower. And my friend's name is Heather. Heather, you want to come out here? Okay. Here's Heather. You want to turn around this way so everybody can see you? I'm going to take this flower and give it to you like this. Now, that wasn't very nice, Heather, was it? Heather, you're such a sweet girl. Here's a real flower for you, all right? Thank you for helping out. Now, we'll come back and check our egg here. And it's quite cold, so I have to try to fish it out using this. And it's so cold that we'll see if it's really cooked. And you see it's quite, well, it's not quite cold, not quite cold. It's I know some of the students are thinking this looks like the egg you have in the dorms. All right, now I want you to take a closer look at the mercury hammer here, which is no longer frozen. You see it's being broken up. It's broken up quite a bit, and it is liquefying because we are not cooling it anymore. So there's the handle, and the mercury is in this trough. So we'll move this out and move on, because it's the Christmas season, move on to a different type of experiment where we're going to trim a Christmas tree. And if you look very carefully, you'll see that I have here the outline of a shape of a Christmas tree, and I'm going to add to this piece of copper a colorless liquid. And as we fill this large beaker with this liquid, we'll see if there are chemical changes that take place. You see we have the whole tree now covered, and we'll look at it and see if there is any evidence of a chemical reaction that's taking place. So we'll come back and look at it every now and then. Now, it's been a tradition in this lecture for me to read a poem. Now, this poem was written by a variety of people. Some of them have contributed good lines, and some of them have contributed not so good lines. I think I contributed the best lines. But I'll let you be the judges, okay? This poem reads like this. Once upon a Christmas dreary, in the lab of Shakhashiri, Christmas you say, and in the lab, most would find it sad and drab, but not in the lab of Shakhashiri, where everything is bright and cheery. Suddenly there was a knock. Shiri stood in a state of shock. You get it? Good. Out from the hood jumped Santa Claus, holding chemistry books in his paws. Santa made me very irate when he dissolved my precipitate. Then he shrieked, "From my helper keep abreast. She's not taking your hourly test. Keep your hands off my sweet blonde. I know about your covalent bond." Santa, while he could, started leaving through the hood. He disappeared with fanfare, and Shakhashiri, standing there, saw an endpoint in the air. That's the end of the poem for this year. Now, we're going to carry out an experiment which involves mixing a variety of chemicals together. We'll move this Christmas tree just to the side a little bit so you can see better. And we'll get a few things out of the way here. And we'll do this experiment in this set of beakers over here. So if you will watch carefully what I'm doing, you will see, maybe, that there are some changes that will take place. So let's go by adding some of this clear, colorless liquid. We add some, and we add some to this, and we add some to this. So far, it's not too exciting. Nothing is really exciting happening except that the volume is increasing, right? And we add some to this, and we have one more. We add some to that too. Okay, and now we'll go back to the beginning and add some more. As we add some more, we'll see if anything happens. And we add some more to this. We'll see if anything happens. And we'll add some more to this. And we'll add some more to this. And some more to that. And some more of this. We'll go back and add some more here, right? More is better, right? Okay, now what we'll do is take a few drops out of this dropper here and add them. You're carefully counting what I'm doing here, right? Okay, and then in order for things to happen, we have to stir them up. So we'll stir this up, and we'll stir this up. Really have to stir them for things to happen. Stir this up too. Stir this up. Stir this up. Stir this up. See, the more we stir them, the more we can make the color disappear. And so we'll go on to a different dropper and add a few drops of this. Okay, we'll go back to our stirring technique. And you see we can restore the colors quite easily. And now, if we do the experiment quite right, we will go back to the original flask that I had. We'll put this up front here, and you watch very carefully with me to see if anything happens as I take these two colored solutions and pour them down here. You see, that's what we do in chemistry. We can make things appear and make things disappear if we know exactly what we're doing. So this series of experiments with the acid-base indicator, series of acid-base indicators, is a very colorful set of experiments, of course, because of the season that we are in now. Now, I want to ask you all to shift your attention to this special part of the lecture table where I have this long spiral tube. And in this long spiral tube, I'm going to mix two chemicals. All right? One is blue in color, and one is colorless. And I'm going to mix those when we turn off the lights. So it's very important for us to do this experiment in the dark. And you watch very carefully to see what happens as we pour these two liquids when the lights are off. Okay? So we'll go. Here we go. This experiment involves the production of light by mixing chemicals, and we call that chemiluminescence. You all have seen the firefly. The firefly reaction is called bioluminescence. Now we can turn the lights on again so we can see our way around. And we do a few more experiments that are quite interesting and also involve chemiluminescence. And to do this one more experiment involving chemiluminescence, I want to call on my associate Fred Juergens to come out and do this experiment. So Fred comes out. And you watch this. He has this long tube. And of course, Fred's going to put his safety goggles on as we do this experiment. And this experiment we're going to do in the dark again. And you pay careful attention to what he's going to do. He's going to light a match and then open the top of this tube and drop the match down the tube, and we'll see what happens. So if we're ready, you turn off the lights, and here we go. You pay careful attention. You'll do it again. of a chemiluminescent reaction. I know it happens so fast. I know it happened very, very fast. And Fred is just taking the tube away. But because it happens so fast, it might be helpful for us to look at it in slow motion, right? So let's look at it in slow motion and see if we can pick out any more details of this experiment. Here we go. There you see the match. I think he got it in this time. And there is the liquid, which is a volatile liquid, and a gas. Okay, now, what we're going to do is take a quick look at the Christmas tree that we started. Let's take a quick look at the Christmas tree and see if it is, oh, there you see. It's beginning to get trimmed. There are decorations on it. And we'll let this go a little bit longer and see what happens. Now, in doing experiments, we try, as I said all along, to make observations. And one of the people who has been paying very close attention to what has been going on here is Dean Cronin. Now, because he's paid so close attention, I think he is qualified now to help me do some of the experiments. Don't you think so? All right. So, Dean Cronin, if you come out here. And I see that you're wearing eye protection, and so you're all set to go. So what I would like to ask you to do is to help me by taking the contents of the beakers in the back row and mixing them with the contents of the beakers in the front row. And as you add the contents, and when you finish adding one set, you start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you start the next one.
All right.
All right? Please.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And you start the next one then. And now count again.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Start the next one. He's doing a good job, right?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Very good, very good.
One, 2, 3, 4, 5, 6, 7, 8, 9, 10.
11.
Wow.
Let's start the next one.
4, 5, 6, 7, 8, 9, 10.
Let's start the next one.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Start the next one. As soon as you start the next one, the color changes. Watch.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Oh, very good, very good.
Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Very good. Thank you very much. Thank you. This is an example of what we call a clock reaction. And the colors appear if we use the same cadence when we're counting. Of course, we weren't doing that. And of course, the colors that we expected didn't always appear on the exact count of 10. But this is an example of a clock reaction. What I want to show you now is an example of a similar kind of reaction, but where the changes are, well, let's see what the changes are. We take this colorless liquid and we add it to this large beaker, and there's a magnetic stirrer there mixing things up. And we add more liquid from a different flask into the same beaker, and then we add the third reagent. And you see that there's a color change already, and still more change, and more change taking place. Now, this is not a clock reaction. We call this an oscillating chemical reaction because the colors continue to oscillate. And one of the fascinating things about chemistry is that we try to understand why this behavior takes place. And that's why we do research, in order to understand this behavior. And we can watch this for a period of time. We can see the color changes. We can see that the duration of each color changes as the reaction proceeds. For example, the blue color now is lasting a little bit longer than it was before. So this is a typical oscillating reaction that we can watch and we can examine and study. Now, what I'd like to ask you to do is to pay close attention to what I have over here, where I have this flask and it has a liquid in it. And what we want to try to do is carry out an experiment by taking the liquid out of this flask and pouring it down on the top of the lecture table. So let's do that and see what happens. You see the liquid is changing to a solid. And this process we call crystallization. We are crystallizing this solid from a supersaturated solution that contains a salt, namely sodium acetate. And you see we can keep doing this. If you have a steady hand, you can make a very long candle-looking object out of it, right? So this is the crystallization of sodium acetate. Let's take a quick look at our Christmas tree and see how our Christmas tree is doing. You see, again, the color of the blue copper ions is coming into view here, and the silver is depositing on the tree, and it looks like a very nicely decorated Christmas tree. Now, in order to keep up the festivities and in keeping with the season that we are in, we need to prepare different ornaments that we can use with the tree. And so to prepare these ornaments, I have asked Fred Jorgens again and my other associate, Vince Jenna, to come out and show us how Christmas ornaments can be prepared. So, fellows, if you're ready, come on out here. And they both have these flasks, large flasks now. They're pouring different liquids into them. And what they will do is carry out a chemical reaction inside each of the flasks. You see, there is evidence of a chemical change already because the color has changed. And what they will do is mix the contents very carefully. You're beginning to see more changes? What kind of changes are you seeing? Yeah, the liquid is turning black, and they continue to shake, and...
No, these are shaking. I'm not shaking.
Oh, they're okay. And the glass is getting to be, what? More shiny, right? And if you watch carefully, you'll see evidence for more chemical change. Sometimes, you know, chemical reactions behave the way you want them to behave. Sometimes they take a little bit longer. That's one of the things that we do when we study chemistry. We learn to be patient, and we learn to be very understanding about controlling the behavior of chemicals. Now, what is happening here is that the inside of each flask, as far as I can see, is getting to be more shiny and more shiny, right? And if they keep this up, as I hope they will, Maybe you're getting too tired. Now you see, what happens is that eventually what they will do is come up with a very big Christmas ornament similar to the one that I have over here. I'll show you what this one would look like. It'll look like this. And what they will be doing, if we carry out this long enough, we will prepare a very large Christmas ornament where we have silvered the inside of each of these flasks. And we prepared this ahead of time, of course, because it's bigger and it takes longer to do. So I think they're probably getting tired from doing this. Maybe you're exhausted. Okay, why don't we set them down now? Let's set them down, and we'll carry out another experiment. This experiment is actually an attempt on our part to show you that you can do a lot of different things with beakers and with chemicals. We've done quite a few different things now, but Fred now is going to show you a different way of using beakers. So watch very carefully.
Oh dear. I lost the tune. I'm going to play one I know, okay?
I want you to take a close look at the Christmas tree here. That's really getting to be quite colorful and quite decorative. And I'm going to carry out a whole series of other experiments, but I think that time is becoming a factor here, and what we ought to try to do is, before we run out of time, for me to express my gratitude to all of you for coming here and for watching this program. And I want to thank Dean Cronin, I want to thank Santa Claus, I want to thank Bucky Badger, and all the boys and girls and the members of the faculty and everybody for being with us tonight and making this a very special evening. Merry Christmas, everybody, and Happy New Year. Don't forget, chemistry can be fun.